The age estimate just came in from the University of Canterbury research team, and the number they're proposing is breaking my brain. 3I Atlas. The interstellar visitor that has been defying explanation since July might be between 8 and 14 billion years old. Let me repeat that. 14 billion years old. Our sun is 4.6 billion years old. Our solar system is 4.6 billion years old. The universe itself is only 13.8 billion years old. And we've got an object passing through our solar system right now that might be older than almost everything we've ever studied, older than our sun, possibly older than our galaxy, maybe even older than the universe itself, which should be impossible, but the data is suggesting it anyway. This isn't speculation. This is coming from Professor Michaeli Bannister at the University of Canterbury in New Zealand, working with Professor Chris Lintott at the University of Oxford. These are serious researchers doing serious analysis, and their preliminary findings are suggesting an age that challenges everything we thought we understood about cosmic timelines. How do you date an object from another star system? You can't exactly drill into it and count rings like a tree. You can't measure radioactive decay without a sample. You're working with remote observations, light that's traveled millions of kilometers, spectroscopic signatures, velocity measurements, and from those observations, you try to piece together a history. Where did it come from? How long has it been traveling? And what conditions did it form under? For 3I Atlas, the age estimate comes primarily from velocity analysis. The object is moving at approximately 60 kilometers per second relative to the sun. That's fast, really fast, faster than most objects in our local stellar neighborhood. When you measure the velocity of stars and objects in our region of the galaxy, you get a distribution. Most things are moving at similar speeds because they formed from the same general cloud of gas and dust. They're part of the same stellar population, same generation, but occasionally you find objects moving much faster or much slower than average. These are outliers, and outliers tell you something about their history. Fast-moving objects are often old. They've been around long enough to accumulate velocity from gravitational interactions. They've been kicked around by close encounters with stars or molecular clouds. Each interaction changes their velocity slightly. Over billions of years, those small changes add up. So when you find an object moving significantly faster than the local average, it suggests it's been traveling for a very long time, long enough to accumulate that excess velocity through countless gravitational interactions. For 3I Atlas, the velocity is high enough that Bannister and Lintott calculated it's been traveling through the galaxy for somewhere between 8 and 14 billion years. 8 billion years at minimum. That's almost twice the age of our solar system. But this object was already ancient when our sun was just beginning to form from a collapsing molecular cloud. 14 billion years at maximum. That's approaching the age of the universe itself. This object would have formed in the very early universe, when the first generation of stars was just beginning to synthesize heavy elements. Think about what that means. If 3I Atlas is 14 billion years old, it formed when the universe was less than a billion years old, when galaxies were still assembling, when the cosmic web was just beginning to take shape. It would have witnessed the entire history of cosmic evolution. It would have been there when our galaxy formed, when our sun ignited, when Earth coalesced from the protoplanetary disk, and now it's passing through our solar system, carrying with it a record of cosmic history that spans almost the entire age of the universe. But here's where it gets really uncomfortable. If the upper end of that age estimate is correct, if 3I Atlas is actually 14 billion years old, it's older than the universe is supposed to be. The universe is 13.8 billion years old. That's measured through multiple independent methods: cosmic microwave background observations, Hubble constant measurements, stellar population ages. All of them converge on 13.8 billion years, give or take a few 100 million years. Nothing can be older than the universe. That's not just a rule, that's a logical necessity. The universe is everything, all of space, all of time, all of matter and energy. There is no before the Big Bang in any meaningful sense. So if 3I Atlas is 14 billion years old, something is wrong. Either the age estimate is incorrect, or our understanding of the universe's age is incorrect, or there's something about this object that doesn't fit into our cosmic timeline at all. Let's go through those possibilities systematically because this is where the science gets really interesting. Possibility 1, the age estimate is wrong. Maybe the velocity-based dating method is flawed. Maybe there are factors that weren't accounted for. Maybe 3I Atlas's high velocity comes from something other than age. This is the most likely explanation. Age estimates based on velocity are inherently uncertain. You're making assumptions about the object's history, about how many gravitational interactions it's had, about the typical strength of those interactions, about the distribution of velocities in the regions it's traveled through.
Solar system, but not impossibly old. That's the conservative interpretation. The age estimate is preliminary. It's based on limited data. It will be refined as more observations come in. And the refined estimate will probably be lower. But here's the thing. Even if the estimate is off by a factor of 2, even if 3I Atlas is only 7 billion years old, that's still remarkable. That's still older than our sun. That's still an object that formed in a completely different era of galactic history. So while the specific number might be wrong, the general conclusion that this is an ancient object is probably correct. Possibility 2. Our understanding of the universe's age is wrong. Maybe the universe is actually older than 13.8 billion years. Maybe the measurements that give us that number are systematically biased. Maybe there's some physics we don't understand that makes the universe appear younger than it actually is. This is less likely, but not impossible. There are ongoing debates in cosmology about the exact age of the universe. Different measurement methods give slightly different results. The Hubble constant, which determines the expansion rate and therefore the age, has been measured to different values by different teams. Some measurements suggest the universe might be slightly older than 13.8 billion years, maybe 14 or 14.5 billion years. That would resolve the tension with 3I Atlas's age estimate. But those measurements are controversial. Most cosmologists think the 13.8 billion year age is solid. It's based on multiple independent lines of evidence. It's not likely to be off by more than a few 100 million years. So while it's possible the universe is slightly older than we think, it's not likely to be old enough to comfortably accommodate a 14 billion year old comet. Possibility 3. There's something about 3I Atlas that doesn't fit our cosmic timeline. Maybe it's not a normal object. Maybe it formed under conditions we don't understand. Maybe it's been preserved in some way that makes it appear older than it actually is. This is the most speculative possibility, but it's worth considering because 3I Atlas has been anomalous in so many other ways. What if the object isn't from our universe at all? What if it's from a previous cosmic cycle? Some cosmological models propose that the Big Bang wasn't the beginning of everything, but just the beginning of our current cosmic epoch. Maybe there were previous universes that collapsed and rebounded. Maybe 3I Atlas is a remnant from one of those previous cycles. That sounds like science fiction. And it probably is. But when you've got an object that appears to be older than the universe, you have to consider exotic possibilities. Or maybe the object has been in some kind of stasis. Maybe it was trapped in a region of space where time passed differently. Maybe it was inside a molecular cloud where it was shielded from cosmic rays and other aging processes. Maybe its apparent age is older than its actual age because of some preservation mechanism we don't understand. Again, speculative. But when conventional explanations don't work, you have to think creatively. The most likely explanation remains that the age estimate is uncertain and will be revised downward as more data comes in. But the fact that serious scientists are even discussing ages approaching the age of the universe tells you how unusual this object is. Let me show you what else the chemistry is telling us. Because the age estimate isn't just based on velocity, it's also supported by compositional analysis. The spectroscopic observations of 3I Atlas show unusual isotope ratios. Isotopes are versions of elements with different numbers of neutrons. The ratio of different isotopes tells you about the conditions under which the material formed. In our solar system, isotope ratios are relatively consistent. Everything formed from the same molecular cloud at roughly the same time, so the isotopic composition is similar across different objects. But 3i Atlas shows isotope ratios that don't match solar system values. The ratios suggest it formed in an environment with a different nucleosynthetic history, different stellar populations, different supernova contributions, different chemical evolution, and some of those ratios are consistent with material that formed very early in galactic history, when the first generation of stars was enriching the interstellar medium with heavy elements, when the chemical composition of the galaxy was very different from what it is today. That supports the idea that 3i Atlas is ancient, that it formed billions of years ago in a very different galactic environment. But here's where it gets even stranger. Some of the isotope ratios don't match any known stellar population. They're not consistent with first-generation stars. They're not consistent with second-generation stars. They're not consistent with anything in our current models of galactic chemical evolution. It's as if the material formed under conditions that don't exist in our galaxy, or that existed so long ago that we don't have any other samples to compare it to. And that brings us back to the age question. If 3i Atlas formed 14 billion years ago, it would have formed when the galaxy was very young, when the chemical composition was completely different, when stellar populations were unlike anything we see today. The isotope ratios would be expected to be unusual. They would reflect conditions that no longer exist, conditions we can only infer from theoretical models. So the chemistry supports the velocity-based age estimate. Both lines of evidence point to an object that's incredibly ancient, older than anything else we've studied in detail. But both lines of evidence also have uncertainties. The velocity-based age depends on assumptions about gravitational interactions. The isotope-based age depends on models of galactic chemical evolution. Both could be wrong. What we need is more data, more detailed spectroscopy, better measurements of the isotope ratios, more precise velocity measurements, more observations that can constrain the age estimate and reduce the uncertainty. And that's where we run into the same problem we've had throughout this entire 3i Atlas encounter. The object is fading. The window for detailed observations is closing. And we're not getting the comprehensive data we need to answer these questions definitively. Bannister mentioned in her analysis that this was a theoretical study. They calculated the age based on velocity just days after the object was first identified. It was a quick analysis to get a preliminary estimate, but preliminary estimates need to be followed up with detailed observations. And those detailed observations require telescope time, spectroscopic campaigns, coordinated efforts across multiple facilities. Has that happened? Maybe, but if so, the results haven't been published yet. We're still working with preliminary data from months ago, still trying to answer questions that should have been addressed with intensive observation campaigns. And now the object is too faint for some of those observations. The window has closed, and we're left with tantalizing hints of an incredibly ancient object, but not enough data to confirm it definitively. That's frustrating, because if 3i Atlas really is 10 or 12 or 14 billion years old, it's one of the most scientifically valuable objects we've ever encountered. It's a time capsule from the early universe, a sample of material that formed under conditions we can only study theoretically. The scientific return from comprehensive study of this object would be enormous. Papers for decades, PhD theses, new insights into galactic evolution, stellar nucleosynthesis, early universe chemistry. But we're not getting that comprehensive study. We're getting scattered observations, preliminary analyses, hints and suggestions rather than definitive answers. And in a few months, the object will be gone, too faint to observe, too far away to study, and we'll be left wondering what we could have learned if we'd mobilized the resources to study it properly. Let me put the age estimate in context by comparing it to other objects we've studied. The oldest stars in our galaxy are about 13 billion years old. These are first-generation stars that formed shortly after the Big Bang. They're metal poor because they formed before supernovae had enriched the interstellar medium with heavy elements. We've studied these stars spectroscopically. We've measured their ages through multiple methods, and they give us a window into the early universe. They tell us about conditions when the galaxy was young. If 3i Atlas is 14 billion years old, it's older than those stars. It would have formed before the oldest stars in our galaxy. It would be a remnant from an even earlier era. The oldest known objects in the universe are certain globular clusters, dense collections of ancient stars that orbit galaxies. Some of these clusters are estimated to be 13 billion years old, or slightly older. If 3i Atlas is 14 billion years old, it's as old as the oldest globular clusters. It's from the same era, the same epoch of cosmic history. But here's the difference. We can study stars and globular clusters in detail. We can measure their spectra. We can determine their compositions. We can model their evolution. We have decades of observations and well-developed theories. For 3i Atlas, we have a few months of observations, limited spectroscopy, preliminary analyses. We're trying to determine the age of an object we barely understand, using methods that have large uncertainties. So while the age estimate is exciting, it's also highly uncertain. It's a starting point for investigation, not a final answer. What would it mean if 3i Atlas really is 14 billion years old? What are the implications? First, it would tell us that objects can survive for incredibly long times in interstellar space. 3i Atlas has been traveling through the galaxy for billions of years. It's been exposed to cosmic rays. It's passed through molecular clouds. It's experienced countless gravitational interactions. And yet it's still intact, still recognizable as a comet-like object, still showing activity when it approaches a star. That tells us something about the durability of these objects, about how well ice and rock can be preserved in the cold of interstellar space, about the timescales over which cometary material can survive. Second, it would tell us about the early universe. If 3i Atlas formed 14 billion years ago, its composition reflects conditions in the very early galaxy. The isotope ratios, the molecular abundances, the structure, all of that is a record of what the galaxy was like when it was young. And that's information we can't get any other way. We can't go back in time. We can't directly observe the early galaxy. But we can study objects that formed back then and survived to the present day. 3i Atlas would be one of those objects, a messenger from the early universe, carrying information about conditions we can only infer from theory. Third, it would tell us about the population of interstellar objects. If one of the first 3 interstellar objects we've detected is incredibly ancient, that suggests ancient objects are common, that the galaxy is full of these time capsules, that we're surrounded by remnants from the early universe. And that would be profound. It would mean that studying interstellar objects isn't just about understanding comets or asteroids. It's about understanding galactic history, cosmic evolution, the entire timeline of the universe. Every interstellar object that passes through our solar system is potentially a sample from a different era, a different stellar population, a different chemical environment. And by studying them, we're essentially doing galactic archaeology, piecing together the history of the galaxy from the objects that have survived to the present day. But all of that depends on the age estimate being correct. And right now, we don't know if it is. The 8 to 14 billion year range is preliminary. It's based on velocity analysis that has inherent uncertainties. It needs to be confirmed with other methods, isotope measurements, detailed spectroscopy, comparative studies with other interstellar objects. And those confirmatory studies require observations we haven't done yet, data we haven't collected, analysis that will take years to complete. So we're in a state of uncertainty. We have a tantalizing possibility, an object that might be older than our sun, older than our solar system, possibly older than the universe itself, but we don't have definitive proof. We have preliminary estimates, suggestive evidence, hints that something extraordinary might be true. And that's where science often lives, in the space between possibility and proof, between hypothesis and confirmation. The age estimate for 3i Atlas is a hypothesis. It's based on reasonable assumptions and solid physics, but it's not confirmed, it's not certain, and it might never be certain, because the object is fading. The window for detailed observations is closing. And we might not get the data we need to confirm or refute the age estimate before it's too late. That's the reality of studying transient objects. You have a limited time to gather data, and if you don't get the observations you need during that window, you lose the opportunity forever. With 3i Atlas, we're watching that window close in real time. Every day the object gets fainter. Every day it becomes harder to observe. Every day we lose the opportunity to answer questions that might never be answerable once the object is gone. And one of those questions is, how old is it really? Is it 14 billion years old? Is it 8 billion years old? Is it younger than that and the velocity-based estimate is just wrong? We don't know. And unless we get more observations soon, we might never know. That's frustrating, but it's also part of the excitement of astronomy. You're working with limited data, limited time, limited resources, and you're trying to answer profound questions about the universe with those limitations. Sometimes you succeed, sometimes you don't, but the attempt is always worth making. The age estimate for 3I Atlas is one of those attempts. It's a preliminary answer to a profound question, and whether it's right or wrong, it's pushing us to think about interstellar objects in new ways, not just as curiosities, not just as unusual comets, but as potential time capsules from the early universe, as messengers carrying information about cosmic history, as objects that might be older than anything else we've studied. And that's valuable. Even if the specific age estimate turns out to be wrong, the idea that interstellar objects can be incredibly ancient is important. It changes how we think about them. It changes what questions we ask. It changes what observations we prioritize. So the revelation that 3I Atlas might be 14 billion years old, whether it's ultimately confirmed or not, is already having an impact on the field. It's making us reconsider our assumptions. It's making us think bigger. It's making us realize that these objects might be more scientifically valuable than we initially thought. And that's progress. That's how science advances, not just through definitive answers, but through provocative questions that force us to think differently. Is 3I Atlas older than our sun? Probably yes. The velocity and composition both suggest it's ancient, older than our solar system, older than most objects we've studied. Is it older than the universe? Probably not. The 14 billion year upper estimate is likely too high. It's probably an artifact of the uncertainties in the velocity-based dating method. But is it old enough to be scientifically remarkable? Absolutely. Even if it's only 8 or 10 billion years old, that's still incredibly ancient. That's still a time capsule from an era of galactic history we can barely study any other way. And that makes it valuable. That makes it worth studying intensively. That makes it worth mobilizing resources to observe comprehensively before it's too late. Are we doing that? Not really. We're observing it when we can. We're analyzing the data we have. We're writing papers and proposing hypotheses, but we're not treating it like the once-in-a-generation opportunity it might be. We're not fast-tracking observations. We're not coordinating global campaigns. We're not doing everything we could to maximize the scientific return. And that's a missed opportunity, because whether 3I Atlas is 8 billion years old or 14 billion years old, it's teaching us something about the universe, about galactic history, about the population of interstellar objects, and we're letting it slip away without getting all the answers we could. That's the reality. That's where we are. An object that might be older than our sun is passing through our solar system right now. And we're watching it fade without fully understanding what it is or where it came from. The age estimate is preliminary, the chemistry is unusual, the implications are profound, and the window is closing. If you want to follow this story as it develops, make sure you're subscribed, because the Jupiter encounter is coming in March, and that might give us one more chance to gather data before 3I Atlas disappears forever. One more chance to answer the question, just how old is this thing? And maybe, just maybe, we'll get the observations we need to find out. Thanks for watching, and keep looking up, because the universe is full of ancient mysteries, and 3I Atlas is one of them.